This is the utility substation. It looks like a water tower. It is a water tower. But we actually weld the same steel we used to make the water tower and build a base around it. And that becomes our environmentally protected area for our proton exchange membranes, internal combustion engines, turbines, offline storage of gases, and stuff like that. These are built every 3 miles. And again, more jobs, more steel. This is the Garden Arbor Light Rail System. Now, we've talked about how we mitigate sewage, how we produce and distribute energy in various forms, and drinking water, etc. Picture Las Vegas for a moment. 1 million people, 3 million toilet flushes a day at a minimum. That's probably 9 million gallons going through their sewer system on a daily basis. When we process that, that's money for us. It's a problem for them, it's money for us. And when we process this waste stream, we actually can create a hydroponic grade solution to grow food. And here we show the Garden Arbor Light Rail System, where the stanchion poles themselves are hollow and have a hydroponic root vessel in them. And we can actually have basically carbon-eating vegetation growing along the whole length of this rail. This is for dense city environments, whether it's in Peru, Lima, and Cusco. We have over 12 million people in each city. Their population is just so dense and the roads are so narrow that they can't really fit anything in like this. But when you take it to the full scale, think of the Sudan, think of Libya, for instance. The nation of Libya, 75% of their food is imported. If anything goes wrong in the global supply chain, the 75% will eat the 25%. This has been known to history. That's why a lot of wars have been fought. So feeding people is one of the most important things we can do. That's what the high rail does. It feeds people. And we do that by taking the waste stream, processing it, making hydroponic grade solutions, raining it down onto sand, and growing either a food grade crop or a fuel grade crop. Doesn't matter to us, it's whatever the local economy desires. So a couple of technical slides. This gives you shows you the range of motion. A lot of people have said, hey, that thing looks like an animal. It's got 4 feet. Well, there's a good reason for that. The suspension system is mounted on a ball joint cantilever suspension arm that gives the whole vehicle the ability to roll, pitch, yaw, heave, dip, and sway, which is the terminology for a Stewart platform or an aircraft simulator. So what I've done is integrated those technologies into this so that no matter how fast the vehicle is going or what the curvature of the rail is, the vehicle itself will always adapt to the G-forces. Not unlike a waiter carrying a tray in a restaurant with a bunch of champagne flutes. He's always going to tilt the tray just right so you don't dump all your wine glasses on somebody on the table. So this whole vehicle has the capability of doing that. And no other system can do that. Here's the kinematic model for the ball joint cantilever suspension system. The square plate you see is actually representative of the bottom surface of the vehicle, structural support. This is the other kinematic analysis shown before. Here is the current structural design for the rail. It's a little bit larger than the one that was illustrated earlier. Some of the FEA models for FEA is finite element analysis. That's the technology used to determine Young's modulus for metals is the deformation under weight over time. So we know what the load capacity is of the steel. This is how we connect all of the pipelines together, trying to determine the efficiency of the flow through the pipeline. We didn't want to have a valve that's bigger than the pipe and then have to flange the pipe down to fit inside the valve. So we reversed it, put the valve inside the pipe, and that's what you see here. It's a very simple mechanism. It's got a large butterfly valve on the inside, and the golden ring that goes around it is a cuff motor. It's a DC stepper motor. It has a built-in capacitor, so if there is ever an attack on the system, or let's just say Mother Nature says, well, I'm going to have a landslide and take a quarter-mile of rail and slide it into the Pacific Ocean off of the California coast. You know, landslides happen all the time. We're dealing with this in Indonesia right now. So this mechanism allows us to cut off the pipeline if the rail is damaged, so we don't bleed out all of our raw materials. I mean, we all know what it's like to have a gas main break. You got a 40-foot column of fire coming out of the ground for like 5 days, and everybody's got to evacuate, and $20 million worth of gas is burned away, and then our insurance goes up. Well, we have these things connecting all of our liquid and vapor-based pipelines together. So very simple device. Talk about the technology behind the motor. This graphically indicates the increase of the magnetic field coming from the rail behind the motor. The motor is in kind of an equilibrium state, maintaining a levitation gap of about 1 inch. But by increasing even by a milliwatt, the amount of current going into the magnet packs behind the motor will give you a lateral force. And so to the right, you see it in cruising, kind of a close-up, you see the coil packs inside the motor, which you'll see again in a moment. And here's where it's slowing down. We just increase the current to the coils in front of the motor and begin to slow it down. In an emergency environment, we can reverse the current in the coils in the motor, grab onto the rail with tons of force, and bring the whole vehicle to a stop rather quickly. So this shows the color thing here is from 0 to maximum intensity of the magnetic flux coming out of the rail, which pushes on the back of the motor. And here is the computer models. Our computer models were done by Integrated Engineering Software in Winnipeg, Canada. They are, without a doubt, the world leader in electromagnetic engineering. Any company, whether it's Ford, GM, Chrysler, Boeing, Lockheed Martin, Northrop Grumman, you name it, they all buy their software from these guys to do their electromagnetic analysis tools. I've known them for years. They did our stuff for us. This shows the coil packs in equilibrium, and this shows them in action. The top illustration shows one of the coil packs. This is the piece that's inside the motor, and in the center is the piece that's inside of the rail. This is a 10-inch long section, which you see 3 of them here along the rail. This one 10-inch piece has the ability to levitate 4,000 pounds of mass. That's 400 pounds per lineal inch. So we have 3 of these individual C-shaped coil packs inside each nacelle, which is a motor that wraps around the rail. So each motor can support 12,000 pounds. And in the lower left is the thrust model, which came out at 13,000 pounds. So we have a vehicle with 4 of these 12,000 pound levitation motors. That's 48,000 pounds of load capacity, but we've got 52,000 pounds of thrust. So we can literally take a 24-ton vehicle and go straight up the side of a mountain if we really want it. So on the financial side, the thing we're dealing with in Lansing and in the capitals of every state is the public-private partnership. Here is a private company, a commercial organization designed to make a profit, building public infrastructure. This has always been done under a public-private partnership. It's been happening for generations. We have offered up a public-private partnership that is literally the most generous in history. We give away 50% of the revenue we make on the public right-of-way, which adds up to enormous tax dollars. We generate our revenue by these 10 primary deliverables. Transit and advertising, yes, that's how public transit makes money, but we make money a lot more ways. Because we have our own energy system, we can run a lot of different subsystems such as sewage mitigation.